Imagine for a second that you're a translator at the United Nations. But instead of translating speeches or like peace treaties between diplomats, your entire job is to translate numbers.
Oh, that sounds incredibly stressful.
Right. And these aren't just arbitrary figures on a spreadsheet. I mean, if you get a single vocabulary word wrong in this numerical language, or, if you misplace one tiny piece of punctuation, an airplane literally falls out of the sky.
Yeah, or a patient gets double the medication they were supposed to receive.
Exactly. Welcome to this deep dive into the art and, well, the science of converting units. We're looking specifically at that chaotic, high-stakes collision between the metric system and U.S. customary units.
It really is a collision, isn't it?
It totally is.
Yeah.
So if you are currently studying for the TEAS or HESI nursing exams, or, if you're just intensely curious about why the United States stubbornly clings to pounds and Fahrenheit while literally the rest of the world has moved on, this deep dive is built for you.
And, on the surface, converting units seems like this purely mathematical exercise, just moving numbers around.
Just boring math torture.
Right, exactly. But looking at the sources we have today, it becomes super clear that this is actually about history, it's about psychology, and really the mechanics of human error.
So our mission today is to unpack how unit conversion actually works at a mathematical level, why the U.S. is trapped in this dangerous split system reality, and why mastering this is a critical safety skill that prevents catastrophic medical and engineering disasters.
It is so much more than passing a test.
Oh, for sure. Because back at school, unit conversion felt like, just endless worksheets of multiplying fractions. But looking through the material, I really want to propose a total reframing for you.
Okay, I'm listening.
Converting units is actually high-stakes language translation. You're taking a physical reality, like a distance, a weight, a volume, and figuring out how to express that exact same physical reality in a completely different language without altering the underlying meaning.
I actually love that analogy because when we talk about converting units, we are expressing the exact same physical quantity just with a different label.
Right, we're not changing the actual thing.
Exactly. We are not changing the underlying amount at all. Like 5 feet and 60 inches are the exact same length in the physical universe.
Yeah, but 1 kilogram and 1,000 grams, same mass.
Yes. Conversion is basically just the arithmetic bridge between two different labeling systems for one real, tangible thing.
So let's get into the mechanics of how we actually cross that bridge.
Yeah.
Because, there's a very specific technique tested heavily on these nursing entrance exams.
Yeah, and the foundational concept here rests on first principles. Basically, you can multiply any quantity by 1 without changing its value.
Which sounds super elementary.
It does, but it is the absolute engine of all dimensional analysis. Think about a conversion factor. Let's take inches and centimeters, for example. The physical distance of 2.54 centimeters is identical to the physical distance of 1 inch. Therefore, if you write that as a fraction, 2.54 centimeters over 1 inch, the value of that entire fraction is essentially just 1.
Because the top and the bottom represent the exact same reality.
Exactly. Dividing a thing by itself equals 1.
So when you multiply your starting quantity by that fraction, you aren't changing the actual size or amount of the thing at all. You are just multiplying by 1, which swaps out the label.
Right. And the formal name for this is dimensional analysis, or the factor label method.
Which always sounded so intimidating to me. But the best way I've found to visualize it is like playing a game of dominoes.
Oh, that's a really good way to think about it.
Yeah, because in dominoes, you have to match the ends perfectly to keep the chain going, right? 5 touches a 5, a 3 touches a 3.
They have to align.
So in dimensional analysis, you are chaining fractions together so that the unwanted units cancel each other out diagonally. Like if you have inches on the top of your first fraction, your next domino, your next fraction, has to have inches on the bottom.
Right, so they match and they cancel out.
Exactly. You just take them off the board. You just keep snapping these dominoes together, canceling units top and bottom until the only word left standing is the unit you actually want.
And mechanically, that's really all it is. You write your starting quantity as a fraction over 1, and you chain your conversion factors exactly like that.
It's so satisfying when it works out.
It is. You arrange them so the units you want to get rid of cancel diagonally. It is a highly reliable, systemic way to prevent errors. Because, if the units don't cancel out properly, you instantly know your equation is set up backward.
You can catch your own mistakes before you even do the math.
Exactly.
But I do want to bring up a friction point I found in the sources, though. This simple domino trick, this multiplying by 1, it doesn't actually work for everything, does it?
No, it doesn't.
Because temperature is the major exception here. When you try to convert Fahrenheit to Celsius, you can't just multiply by a fraction like you do with inches and centimeters.
No, you can't. Temperature operates under a totally different set of mathematical rules. Converting between Fahrenheit and Celsius involves what mathematicians call an affine transformation, not a proportional ratio.
An affine transformation. Okay, break that down for us.
Basically, unlike length or mass, the Celsius and Fahrenheit scales do not share a common 0 point.
Right, which means 0 inches is the exact same physical reality as 0 centimeters. It's just nothing, no distance.
Yes, exactly. But 0 degrees Celsius is the freezing point of water, which is 32 degrees Fahrenheit. They start at completely different baselines.
So they don't agree on where 0 is.
Right. And because of that, you must account for that 32-degree offset before you can scale the numbers. You have to add or subtract 32.
Okay, so what's the actual formula then?
The formula to find Fahrenheit requires taking the Celsius temperature, multiplying it by 9/5, and then adding 32 at the end. If you try treating temperature as a pure ratio conversion, like a domino, you will get a wildly inaccurate answer.
And clinically, that matters tremendously. Like, if a patient spikes a fever to 39 degrees Celsius, a clinician has to compute that accurately and immediately. Because most international literature and, hospital equipment use Celsius. But U.S. patients only understand how sick they are if you tell them their fever is 102.2 degrees Fahrenheit.
That constant need to translate back and forth is a daily reality in American healthcare. And really, it forces us to look at the historical context of how we even ended up in this mess.
Yeah, why do we have this split system? I know unit conversion as a daily problem isn't a modern invention. Ancient merchants had to figure it out for trade. But the current tension between metric and customary was created deliberately, right?
It was. It really traces back to the French Revolution.
The 1790s in France was a period of absolute chaos. And looking at the sources, one major source of that friction was their lack of a unified measurement system.
Oh, it was a nightmare.
The sources indicate there were roughly 250,000 different units of weight and measure in use across the various regions of France at the time.
250,000. Just let that sink in. It was a logistical nightmare for trade, for governance, for everything.
How did anyone buy or sell anything?
Barely. Measurement was heavily based on local custom, and the definitions shifted from town to town. Some units were quite literally defined by the physical length of a particular local king's foot.
Which is objectively hilarious, but so impractical. So the French Academy of Sciences was tasked with fixing this.
Right. Brilliant minds of the era, like Jean-Charles de Borda, Joseph-Louis Lagrange, and Antoine Lavoisier, they all set out to create a rational, universal system.
And I read that they specifically wanted a system based on nature, right? So that no single monarch or nation could claim ownership of it.
Exactly. They sought natural constants that would remain true regardless of political upheaval, so they defined the meter as 1/10,000,000th of the distance from the North Pole to the equator.
Wow.
Yeah, along the meridian passing through Paris specifically. And they defined the kilogram based on the mass of a specific, precise volume of water.
And crucially, they built the entire system on powers of 10.
Yes, which was the genius part. The whole point of the metric system was to make conversion a simple matter of just moving a decimal point left or right, millimeters to meters to kilometers.
Instead of having to memorize that there are 12 inches in a foot and 3 feet in a yard and 5,280 feet in a mile.
Which is so arbitrary. The metric system was designed from the ground up to be mathematically elegant. It was a monumental achievement of rationalism.
And throughout the 19th century, this metric system spread rapidly across Europe.
It did. Meanwhile, the English-speaking world was going in a totally different direction. Britain standardized its own customary units into the imperial system in 1824.
But the United States had already diverged from British units before that 1824 standardization, didn't they?
I did, yes.
Which creates one of those quiet error traps that I found absolutely fascinating. A U.S. gallon and a British imperial gallon are actually not the same thing?
Not at all. A U.S. gallon is approximately 3.785 liters, whereas an imperial gallon is larger. It's about 4.546 liters.
Wait, really? So even within the non-metric world, different nations were speaking completely different dialects of measurement?
Exactly. It wasn't just metric versus customary. It was customary versus imperial, too.
Now, the U.S. did make an attempt to unify with the rest of the globe eventually. Congress passed the Metric Conversion Act in 1975, declaring metric the preferred system for trade and commerce.
They did, but there was a massive catch.
Yeah, they made it completely voluntary. There was no mandated timeline whatsoever.
And as a direct result of that voluntary approach, the United States remains one of only 3 countries in the world today, alongside Liberia and Myanmar, that has not officially adopted the metric system for everyday use.
Which is just wild. So the everyday American uses pounds, miles, and Fahrenheit. But U.S. medicine, U.S. science, and the U.S. military had to go metric in order to interact with the international community.
I had no choice.
Right. So when you walk into a hospital today, you walk in speaking customary. You know your weight in pounds, your height in feet and inches.
But the hospital machinery, the diagnostics, the pharmacy, all of that runs entirely on metric.
Yeah, the drugs are dosed in milligrams and kilograms.
Mm-hmm.
So this split system environment has to place an immense cognitive burden on healthcare workers.
Oh, it really does.
I mean, nurses are basically border patrol guards. They're stationed right at the exact seam between the patient's customary world and the hospital's metric world.
That is a perfect way to describe it.
They literally have to translate the patient's physical body into numbers the hospital's pharmacy can actually use.
And that cultural stubbornness, the refusal of the broader society to adopt the scientific standard, it forces medical professionals to perform constant mental gymnastics at the bedside.
Which is exhausting.
It is, and it's precisely why unit conversion is a gatekeeping competency on nursing entrance exams like the TEAS. You cannot be a safe practitioner unless you are a flawless translator.
Because the stakes for failing to translate at that border are catastrophic. Let's look at pediatric medication dosing for a second. This is the exact kind of scenario tested on nursing exams, but it plays out in emergency rooms every single day.
It does. Consider a physician ordering a weight-based dose of a medication, let's say 15 milligrams of drug per kilogram of the patient's body weight.
Okay, 15 milligrams per kilogram. And let's say the child sitting on the exam table weighs 40 pounds.
Right. So the drug is dosed in kilograms, but the kid's weight was recorded in pounds.
So if a tired nurse or maybe a flawed electronic health record system skips the conversion step and simply takes the 40 pounds and multiplies it directly by the 15 milligrams.
The math balloons instantly. The conversion factor is 1 kilogram to 2.2 pounds. By failing to divide that 40 pounds by 2.2 to get the correct weight, which is 18.2 kilograms, the system treats the child as if they weigh 40 kilograms.
Oh, wow. So the child receives roughly 2.2 times the intended dose.
Yes. It is a massive, potentially lethal overdose.
Just from one skipped math step.
Mm-hmm.
And this category of error dosing by pounds when the reference range is in kilograms or vice versa is one of the most thoroughly documented sources of pediatric medication errors in hospitals.
Absolutely.
But this failure to translate across systems isn't just a healthcare problem. The engineering world has its own legendary disaster. The Mars Climate Orbiter in 1999.
Oh, that one still hurts to think about.
NASA lost a $327.6 million mission simply because 2 teams failed to communicate across measurement systems.
Yeah. The engineering team at Lockheed Martin, who built the spacecraft in Colorado, calculated the thruster firing force using U.S. customary units, specifically pound-seconds.
But the navigation software, which was managed by NASA's Jet Propulsion Laboratory in California, was programmed to expect that incoming data in metric units, Newton seconds.
So one team spoke customary, the other spoke metric, and the computer system in the middle didn't have a translator.
It just blindly absorbed the raw numbers.
Exactly. The software interpreted the smaller pound-second values as if they were the larger Newton-second values. And over the course of the 9-month journey to Mars, these tiny miscalculations compounded.
It's just devastating.
It really was, because when the orbiter finally fired its main engine to enter Mars's orbit, it approached at an altitude of about 57 kilometers above the surface.
And the flight plan called for an approach of 140 to 150 kilometers.
Right. So it went way too deep into the Martian atmosphere and just burned up.
It just proves that conversion isn't just a homework annoyance for students. It is a critical vulnerability in complex systems.
And we saw the exact same vulnerability nearly cause a massive loss of life with the Gimli glider in 1983.
Oh, right. Air Canada Flight 143. That was a Boeing 767 that ran completely out of fuel mid-flight over Canada.
Yes, because at the time, Canada was in the middle of a national transition to the metric system.
So they were straddling both worlds.
Exactly. This particular 767 was one of the first in the fleet that was supposed to be fueled using metric measurements, liters, and kilograms. But The plane's automated fuel information system was broken.
So the ground crews had to calculate the fuel load manually using a dripstick.
Right. And the ground crews and pilots were still accustomed to the old system of imperial gallons and pounds.
Oh, I see where this is going.
Yeah. When they calculated the mass of the fuel they had just pumped, they used the customary conversion factor of 1.77 pounds per liter instead of the correct metric conversion factor of 0.803 kilograms per liter.
So they treated a metric measurement as if it were a customary one.
Precisely. And as a result, the aircraft took off carrying less than half the fuel it actually required for the journey.
That is terrifying. It literally became a 156-passenger glider at 41,000 feet.
It did. Now, the pilot miraculously managed to land it on a decommissioned runway in Gimli, Manitoba, so everyone survived.
Thank goodness. But the Mars orbiter and the Gimli glider illustrate such a predictable hazard, right? Mixing measurement systems mid-transition is exceptionally dangerous.
Very dangerous.
Whenever an organization or a society straddles metric and customary units, the risk of failure just skyrockets. People think they can just eyeball numbers if they look close, like they do at the grocery store.
But an estimation might be fine when you're buying deli meat. In engineering and healthcare, estimation is a load-bearing failure waiting to happen.
The danger of mixing systems is clear. But, as I dug into the research, I realized that some of the most dangerous traps are actually hidden within the systems themselves or just in the way we talk about them.
Oh, absolutely.
Like there's a massive misconception about mass versus weight.
Yes. In everyday language, and even in clinical nursing practice, we treat kilograms and pounds as directly interchangeable.
Right.
But from a physics standpoint, they are fundamentally different concepts.
Mass, which is measured in kilograms, is intrinsic, right? It's a measurement of how much actual matter makes up an object.
Correct. But weight, which is measured in pounds or newtons, is a force. It depends entirely on gravity pulling down on that mass.
So that crusted conversion factor we rely on, the 2.2 pounds per kilogram, is merely a practical simplification.
Yes. It is only mathematically true on Earth at standard gravity. If you take an object to the moon, its mass in kilograms remains exactly the same, but its weight in pounds drops drastically because the gravitational pull is weaker.
Which is wild to think about. Obviously, for the purposes of an HESI exam, you convert them directly, but knowing they are not physically equivalent is vital for deeper scientific literacy.
It really is.
Then there's a terminology trap that I found fascinating. Let's look at cc versus ml, a cubic centimeter and a milliliter.
This is a great example.
Because watching medical dramas on TV, there is invariably a scene where a doctor runs down a hallway yelling, "Push 50 cc's stat."
Every single time.
Right. So I looked into why the Joint Commission, which is a major healthcare safety organization, has pushed so hard to eliminate the term cc from hospitals. I assumed it was like a complex mathematical conversion issue.
Nope. Mathematically, no conversion is needed whatsoever.
Really? No?
None. A cubic centimeter and a milliliter are numerically identical. 1 cc is exactly 1 ml.
They define the exact same volume of three-dimensional space.
Exactly. So the ban on the term cc has nothing to do with math and everything to do with human handwriting.
Of course. When a doctor scribbles cc hastily on a prescription pad, a rushed pharmacist or nurse can easily misread those two loopy C's as a U, which stands for unix.
And that is where the danger comes in. A physical dose of 50 cc gets visually misinterpreted as 50 units of a completely different medication, like insulin or heparin.
And the resulting errors are devastating.
Very much so. The mandate to use ml instead is strictly about visual legibility and error prevention on the page. It is a debate about notation, not volume.
So television doctors are actually yelling outdated, dangerous terminology just for dramatic effect.
Pretty much, yeah.
But there's another trap that genuinely shocked me. And it happens entirely inside the otherwise safe, rational metric system. It's the 1,000-fold metric trap.
Oh, this is a big one.
Because confusing pounds and kilograms causes a patient to get double the dose. But confusing milligrams and micrograms is a 1,000-fold difference.
It is arguably the most terrifying failure mode in modern healthcare.
Explain how that happened.
Well, the elegance of the metric system is its use of prefixes to scale up and down. Milli means 1,000th. Micro means 1/millionth. Therefore, a milligram is 1,000 times larger than a microgram.
So if a physician orders 50 micrograms of a powerful cardiovascular drug and a nurse misreads the abbreviation MCG as MG or, just misplaces a decimal point by 3 spots during a calculation.
The patient receives 1,000 times the intended dose.
1,000 times.
Yes. The outcome of a 1,000-fold overdose is almost universally fatal. The old apothecary units like grains and drams caused confusion, which is why they were phased out.
Right.
But this microgram to milligram error happens within the modern standardized system, all because of one tiny misplaced dot on a digital screen or a piece of paper.
It all comes back to being that rigorous translator. One wrong syllable, one missed decimal, changes the entire physical reality.
It really does.
So let's distill the core takeaways for you from today's deep dive.
First, remember the golden rule. Dimensional analysis is just multiplying by 1. A conversion factor is a fraction where the top and bottom are physically equal.
Right, you use that domino effect to cancel unwanted units diagonally, ensuring your labels are correct before you ever touch the calculator.
Exactly. Second, remember the temperature exception. Because Fahrenheit and Celsius have different 0 points, they are in a fine transformation.
So you can't just multiply. You have to add or subtract that 32-degree offset.
Yes. And third, never underestimate the real-world consequences. Mixing measurement systems without a reliable translator or misplacing a decimal within the metric system has literal life-or-death stakes.
The Mars orbiter burning up, the Gimli glider running out of fuel, pediatric dosing errors, these are all fundamental failures of translation.
They are.
Whether you are staring down a complex ratio question on the TEAS exam, trying to remember if you divide or multiply by 2.2, or even if you're just at home in the middle of the night measuring over-the-counter liquid acetaminophen for your child with a kitchen spoon instead of the calibrated syringe.
You are participating in this high-stakes translation.
Exactly. Mastering it doesn't just get you a passing grade. It makes you a safer, more competent participant in a world governed by physical laws.
It provides you with rigorous control over your physical environment, ensuring that the intent of an action matches the outcome, regardless of the labeling system you happen to find yourself in.
Well said. But before we wrap up, there's one final provocative thought. I want you to mull over something that builds on everything we've explored today.
Oh, I'm intrigued.
We established earlier that the 2.2 pounds per kilogram conversion factor is merely a practical simplification. It only works here on Earth because weight changes with gravity, while mass remains constant.
Right, the math is fundamentally tethered to Earth's specific gravitational pull.
And human habit is so culturally entrenched that the United States has kept this dangerous dual measurement system alive for centuries, despite losing expensive spacecraft and causing tragic hospital errors.
That's true.
So what happens when humanity eventually sets up permanent medical clinics on the moon or on Mars?
Oh, wow. The physical environment will instantly break our customary habits.
Exactly. The moment a nurse steps foot in a lunar hospital, gravity changes. That trusty 2.2 pounds per kilogram conversion factor we rely on every single day to safely dose medicine will instantly become completely useless.
Because a patient's mass will be the same, but their weight in pounds will be a fraction of what it was on Earth.
Right. So, will our stubborn, split system reality follow us into the solar system? Are we going to force future generations of nurses and engineers to rewrite the textbooks and memorize new gravitational conversion factors just because we refuse to fully learn the metric language back on Earth?
That is a terrifying thought.
It really is. So the next time you are converting a patient's weight, remember, you aren't just doing math. You are the border guard. Make sure nothing dangerous gets across. Thanks for joining us on this deep dive. See you next time.